low redshifts, there is lots of nonlinear structure on small scales, so we can't disentangle the initial conditions. And the bigger the volume is that we probe, the better are the statistical constraints we put on the initial conditions, because you just ask how many independent regions of a size comparable to the wavelength of a given Fourier mode we can fit inside the survey volume. So the bigger the survey volume is, the more independent regions we probe, and the better are the statistical constraints that we have. So most of the volume of the universe is above redshift 5, and that's why we should map it. Of course, from the cosmic microwave background, we have information that there was already activity. There were stars forming in the universe at redshifts above 5, simply because of the optical depth for Thomson scattering that is inferred after a redshift of 1100. And that is detected in the form of large-scale polarization anisotropies, which could only be generated when the horizon of the universe subtended a large enough angle corresponding to these anisotropies. So at a redshift of 1,000, the horizon was of order a degree, and such anisotropies on very large scales could not have been produced. The only way to produce coherent anisotropies in the polarization on large scales is to scatter the microwave background at low redshifts. And in this case, it's redshift of order 10 or so. And so the indication from this optical depth for Thomson scattering is that the very first stars and galaxies formed less than 500 million years after the Big Bang and ionized the universe at that time. Now, an important effect that was considered only over the past year or so is the fact that the baryons have a different velocity when they are released from the microwave background at redshift 1100. And this is an effect that was worked out by Dmitry Tseliakovich and Chris Hirata. Dmitry is here sitting over there. And the effect is very simple. At redshifts above 1,000, the radiation had sound waves in it. And the speed of sound in radiation is the speed of light divided by the square root of 3. So you get acoustic waves oscillating in the universe. And these acoustic waves basically oscillate on all scales up to the horizon divided by square root of 3. And the baryons are oscillating together with the radiation until they decouple, until the hydrogen forms from recombination of electrons and protons. But at that point, the dark matter, of course, doesn't care about the radiation, so there is relative streaming of the baryons relative to the dark matter. And the characteristic amplitude of this velocity is of order 30 kilometers per second at a redshift of 1,000. And of course, this streaming has an important implication on small scales. Imagine a dark matter perturbation collapsing on very small scales. Of course, if the baryons are streaming relative to the gravitational potential well, they will not fall into it if the velocity is bigger than the depth or the escape speed from the potential well. And these regions where the baryons are moving are of order a few co-moving megaparsecs. So they are much bigger than the gene scale that corresponds to the smallest objects that form at high redshifts. But if you take this into account, in other words, if you associate an effective sound speed, which is the actual sound speed of the gas plus the streaming velocity, then you do suppress structure formation on scales smaller than 10 to the 6 solar masses, on halos that correspond to the very first condensations of gas. And you can sort of see it here, depending on the streaming velocity. This is at a redshift of 100, the streaming velocity is 3 kilometers per second. So that's the RMS. And of course, 2 sigma fluctuations would have 6 kilometers per second. However, you can see here, this is the halo mass that is affected as a function of the streaming velocity. And of course, as you go to high streaming velocity, the minimum halo mass that is able to assemble baryons goes higher. But the effect is mostly pronounced, and this is the redshift. At redshift 10, for example, the effect is only significant for halo masses below 10 to the 6. So that means that only molecular hydrogen cooling is affected by this, halos that cool by atomic hydrogen cooling, which is assumed to be the dominant cooling mechanism during reionization, are not affected because they have a minimum virial temperature of 10 to the 4 degrees Kelvin or a halo mass of order 10 to the 8 solar masses at redshift 10. So I would say for the standard discussion on reionization that assumes atomic hydrogen cooling, because molecular hydrogen is very fragile, the minute you produce UV background, it gets dissociated quite easily. If atomic hydrogen cooling is the important cooling, then there is very little effect of this relative streaming. Okay, but if molecular hydrogen cooling is important, then of course it makes a difference. And of course there could always be mini halos that have gas in them that don't make stars that absorb UV photons. So for that purpose, these mini halos might have an effect on, as sinks for the ionizing photons during reionization. Now the first dwarf galaxies, of course, the first halos that made stars were very small. As I just mentioned, they were afforded the Jeans mass 10 to the 5 solar masses, comparable to the mass of a globular cluster. And they formed at the intersection of sheets and filaments. And you can imagine two basic ways of mapping the distribution of matter in the early universe. One is to basically survey these sources of light, these clusters of stars. If there are many stars in them, we call them galaxies. If there is only one star in a dark matter halo, some people are not sure how to call them, but it doesn't matter how you call them. We know what they are. They are single stars surrounded by dark matter. So I don't think we have to get into the issues like what is a planet in the solar system in the context of cosmology. We don't need to define what a galaxy is. It's enough to know what we are talking about. And so one way is indeed to use a big telescope in the infrared and survey the distribution of sources of light. Another way to map the distribution of matter is to survey the diffuse gas in between the galaxies. And at high redshift, most of the baryons are still in between galaxies. Now, the one thing to keep in mind, which theorists did recognize 7 years ago, what I mean by theorists are people that do analytic calculations. The numerical people just recognized it a few years later. And the point is very simple. The very first galaxies to form, say, at a redshift of 20 were highly clustered, just like the tallest mountain peaks in the Himalayas that sit on top of a ridge, right? So they are highly clustered. So that was known. This is the idea of bias. But what was not recognized is the scale over which you get very large clustering. And the scale turns out to be 100 co-moving megaparsec, a very big scale. And people that did the numerical simulations of reionization early on used boxes of order a few megaparsec and claimed that they get the correct answer. And they found that reionization occurs very rapidly. Of course, if you take one single atom, it will occur instantaneously, reionization. So the point is you need a box that is as big as 100 co-moving megaparsec to get a fair sample of the universe at those very high redshift. And that's a challenge for numerical simulations, because on the one hand, you need a very large box, but on the other hand, you need to resolve these tiny dwarf galaxies that are much smaller than the galaxies we find nowadays. And therefore, you need a huge dynamic range to perform these simulations. In addition to solving for the gravitational field as a function of time, you need to do the hydrodynamics and the radiative transfer, as well as the chemistry if you want to worry about the molecular hydrogen. And that's very challenging, but it's being done these days. And only over the past couple of years, it was done reliably. Before that, the boxes were much too small, simulation boxes. And so there is a generic evolution that many of you have seen for the ionized regions during reionization. And I'll show just one simulation that was done by heat track, but there are many of them, and they look quite similar. So there is no point in showing all of them. You see the red regions first forming around the filaments. These are the ionized regions, and then eventually they overlap and make the entire universe ionized. Just like a first-order phase transition where you have nucleation sites, these are the positions of the galaxies. Now, what's new, what came out over the past year in terms of the first stars. Let me just mention two highlights. One is that in the very distant past, the people that do simulations of the first stars, and they zoomed into these very small gas clouds, they were able to follow the collapse of a single star, the very first stars, population 3 stars, and they were claiming that there is no fragmentation. You end up with one star. But now, when they have better numerical techniques, it seems like the core that was supposed to make a single star breaks. And usually it breaks at least into 2 clumps. And you get a binary. But in fact, there are 2 recent papers arguing that, in fact, you get multiple stars. So just like star formation in the local universe, you end up with multiple seeds which accrete gas from the surrounding cloud. Now, these simulations cannot follow the evolution beyond 1,000 years or so due to numerical limitations. And you want to follow the evolution to millions of years, which is the characteristic lifetime of these very first massive stars. So we don't know whether these multiple clumps eventually join together. Maybe some of them are ejected due to dynamics. But one thing is clear, that you don't necessarily end up in a single star. And that has implications, for example, for gamma ray bursts. So these are just 2 papers from 2 independent groups that reported that, but there are more of them more recently. The other interesting result is that if you consider the spin of these very first stars, they actually turn out to have a lot of spin because the gas accretes onto them typically through a nearly Keplerian disk. And that means that they are fast rotators. And again, that has implications for their potential as serving as progenitors of gamma ray bursts. And in fact, there was a Nature paper just a couple of weeks ago reporting about evidence for high spin in the first generation of stars. And that evidence came from abundances of strontium and yttrium in 8 old stars that are as old as 12 gigayears in NGC 6522. That's an open cluster in the Milky Way. And to explain the observed abundances, they required very significant mixing that you get only from very fast rotation of the stars that enrich those old stars. So let me discuss now the diffuse gas in between the stars. And of course, the traditional way of probing the diffuse gas in the intergalactic medium is using quasar absorption spectra, using the Lyman alpha absorption line along the line of sight. The problem is that quasars become very scarce as you go beyond redshift 6.5 or so, and it's very difficult to find them. You need bright quasars, very high mass black holes that do not exist simply because galaxies were not very massive at early times. So we need another way of probing the gas. Of course, one way to do it is with gamma ray bursts. Gamma ray bursts rely on a single star, and a single star doesn't get dimmer as you go to higher redshift intrinsically. So that's one way of probing the intergalactic medium. But there is another way, and that's basically using the 21 centimeter line of hydrogen. So as you all know, if the spin of the electron is aligned with the spin of the proton, you get a higher energy state than if it's anti-aligned, and the transition is associated with the emission of a photon of a wavelength of 21 centimeter. And since we are here at Harvard, I should mention just some anecdotes about the connection to Harvard. Lyman was actually a person. The Lyman series is called after, he was actually the head of the physics department down the road here at Harvard. And there is actually a building named after him. And he discovered experimentally the Lyman series. And then, of course, Cecilia Payne-Koposhkin. She was actually the first chair of the astronomy department here. And she, in her PhD, discovered that the sun is made mostly of hydrogen. And Henry Norris Russell actually argued against her, saying that she must be wrong. And then he realized that she was right. And the people at Princeton still prefer to believe that he actually confirmed the existence of hydrogen in the sun, although it was Cecilia that did it. Ed Purcell, after 21 centimeter, the 21 centimeter line was theoretically predicted by van der Havel, he simply opened the window in his office in the physics building and stuck a horn antenna through that window and looked at the Milky Way and found the 21 centimeter line from the Milky Way. So there is still a plaque under the window of his former office. I mean, it's in the physics department. If any of you is interested, you just go to the physics department. You can find this plaque about the detection, the first detection of 21 centimeter. And of course, George Field was involved in arguing that the 21 centimeter line can be useful in probing cosmology. And George was the first director of the Center for Astrophysics here. So we just discussed this 21 centimeter line, and one defines the spin temperature to be simply the excitation temperature that defines the occupation of the upper state relative to the lower state, given that the transition energy is 0.07 degrees Kelvin in energy. And of course, the spin degeneracy factor is 3 for this transition. And there are two ways of exciting the transition. One is through atomic collisions or Lyman alpha coupling, and both of those couple the spin temperature to the kinetic temperature of the gas. But then there is also the radiative coupling to the microwave background, which couples the spin temperature to the microwave background temperature. And of course, the two temperature, the kinetic temperature and the microwave background temperature, could be different. And the idea of 21 centimeter tomography is that we observe this wavelength at longer wavelengths. So at the redshift of 9, at Z of 9, this wavelength is actually 2.1 meters. And that's roughly the height of the tallest basketball player, right, in the NBA. We can probe different redshifts by slicing the universe, just like slicing Swiss cheese. And that's a simple illustration of how these very first ionized bubbles formed and eventually overlapped. And this is a more scientific map of what happened, produced by Jonathan Pritchard in a News and Views paper that we put a few months ago in Nature. And you can see blue here is an absorption signal. Red is an emission signal. So early on, after a redshift of 200, the baryons decoupled thermally from the microwave background and were cooler than the microwave background. So you get a spin temperature or a brightness temperature that is lower, that is negative relative to the microwave background. So these are the dark ages before the first stars formed. And then early on, the coupling was through collisions. The coupling of the spin temperature to the kinetic temperature of the gas was through atomic collisions. Then, because the universe expanded, the density of the gas got diluted to the point where coupling to the microwave background won over atomic collisions. And then the spin temperature went back to an equilibrium with the microwave background, at which point there was no contrast in the brightness temperature relative to the microwave background. So you can see this as the black region here. But completely coincidentally, the very first galaxies formed around that time. So there is this black region, but it's very short-lived, because we expect, according to the standard lambda CDM cosmology, that the very first galaxies formed around that time and produced X-rays that heated up the gas. But more importantly, they produced UV radiation that first coupled the spin temperature again to the kinetic temperature of the gas, which at this point was even lower than it was earlier. So you get an even deeper absorption trough until the X-rays heat up the gas above the microwave background. And then from then on, you get the signal in emission. Now, this is the global signal, what you see here. This is basically a spectrum of the sky. You integrate across the sky, don't care about fluctuations across the sky. You integrate across the sky, and you just consider the brightness as a function of frequency, which is equivalent to redshift. So this is the spectrum of the sky. And this is called also the global signal. And once reionization ends, once all these ionized bubbles overlap, we get back to this black region here, which is the end of reionization. So one would expect people to go after this global signal first before they go after the fluctuations. And you can see here that the global signal itself is actually sensitive to various parameters in this problem. For example, how much X-rays were produced per star formation rate in the early universe. And this is parameterized by the parameter fx here, and a value of order unity implies an efficiency for producing X-rays similar to that we see in nearby galaxies. Okay, and if the early galaxies were more efficient in producing X-rays, which you might expect based on the fact that the stars were more massive, and therefore, if you had binaries, you had more black holes around that would produce X-rays, stellar mass black holes. Then, of course, the history changes. So, in fact, you can, in principle, avoid this very deep absorption trough in the global signal by heating the gas early. You can also avoid it by heating it through dark matter annihilation, for example. There is another parameter which is represents the efficiency of producing UV photons, or Lyman alpha coupling. And of course, the bigger that is, the deeper is, or the earlier is the absorption trough. So these are parameters that we could, in principle, measure if we measure this global signal. Okay, and you can see here what happens if there are no stars, for example. You don't get this dip, the second dip. And if there is no ionization, you end up with some signal that looks like this. So obviously, we can learn a lot about the history of reionization just from measuring this global signal at these frequencies here. And as often is the case in science, the big teams or most of the community is working in a single direction without much variation, and you find only a couple of pioneers that go in a different direction. So in this case, for the global experiment, it's Alan Rogers that will speak on Friday, and Judd Bauman. I don't know if he's here already. But at any event, they did the experiment. They got the first results from this experiment, a single dipole integrating across the sky, and they basically constrained the global signal and how rapid reionization was. Of course, the biggest hurdle is foregrounds, and this is a very nice illustration from Liu and Tegmark that are supposed to speak tomorrow, so I'm sure they will cover some of this. You can see point sources, and that's the redshift direction here. So continuum sources look like lines in this box, the data box that we are probing. Of course, there is detector noise and galactic synchrotron emission, which is extremely bright, 4 to 5 orders of magnitude more than the signal that we are seeking. But it's smooth as a function of frequency. And that's a very important feature that allows us to remove it. And Bauman and Rogers were able to, in a Nature paper just 6 months ago, or a bit less, were able to put a lower limit on the duration of reionization. So the width in redshift space of reionization must be larger than 0.07 or so, or 0.1, roughly speaking, at 1 sigma. And that corresponds to 10 million years or so in real time if you calibrate it at redshift at a redshift of order 10. Of course, it's not surprising theoretically because that's the lifetime of massive stars. So unless you made all the massive stars exactly at the same time in the universe, you would never be able to have reionization have such a short duration. But it's nice that we already have a constraint, an empirical constraint. And of course, this can be improved with future instruments. This instrument was relatively cheap, just a few $100,000. So It's 2 orders of magnitude less expensive than the big experiments that we will discuss this week. And the reason they are sensitive only to very sharp reionization histories is because that would produce a sharp spectral feature in their global signal. And of course, one is really interested in the 3-dimensional mapping of the hydrogen in the universe. And for different K modes, you get different evolution of the amplitude as a function of redshift. So here we show just the amplitude as a function of redshift from a review paper we had with Jonathan Pritchard. And of course, there is also the effect of peculiar velocities that many of you are familiar with. So the optical depth for the 21 centimeter line is, of course, proportional to the density of hydrogen at resonance, but is also inversely proportional to the velocity gradient, just like in the Sobolev approximation. And the velocity gradient is modified. Usually, it's the Hubble parameter. V is proportional to R locally. But it's modified if there is a density enhancement. And the correction is of order the correction that you get for the density. And then there is an angular dependence that is familiar from galaxy surveys, the so-called Kaiser effect, where if you consider a K mode at some angle relative to the line of sight, then this the angle of the K mode appears in the amplitude of the mode. And you end up with a cosine square theta dependence in the power spectrum. And that is squared. So you end up with terms that are of order cosine to the 4th cosine square. And if you isolate these terms, you can in principle infer the peculiar velocity, which is induced only by gravity. And therefore, it measures something about the initial conditions of the universe, irrespective of the astrophysics. And this is an illustration of the Murchison wide field array, one of the experiments that are being done. The reason I put it up is because NSF decided not to add funds to it as of last week. And so instead of 500 antenna tiles that I had in the original slide, now it's based on the funding that is expected from Australia, it will have only 128 tiles. So the people involved in this experiment will have to rethink how much information or what's the best strategy to extract the cosmological information from an array that is reduced by a factor of 4. And of course, there are other experiments, and people in the audience are involved in them, and we will hear more about them later on. I hope they are doing better in terms of funding. And of course, one would like to separate the physics from the astrophysics. And this, I don't mean to be to say that in a degrading fashion with respect to astrophysics. There are some astrophysicists in the audience, and I'm not trying to insult them. But what I mean by astrophysics is basically anything to do with star formation. And that's messy. We can't really simulate star formation from first principles, starting from the initial conditions from inflation in a way that will give us a robust answer. It's a complicated process. And so if we see stars, we can't invert the problem. We can't figure out the initial conditions from inflation or the nature of the dark matter and dark energy by looking at stars. And so what we would like is other ways of probing the initial conditions from inflation, the nature of the dark matter and dark energy, without relying on stars. And that means separating physics from astrophysics. And of course, we can do that before the first galaxy is formed. So the microwave background anisotropies represent one way of doing that. And that can be done if we detect the 21 centimeter, for example, the global signal above redshift 20 or so. During reionization, if we figure out a way to pick out the peculiar velocity effect, which is actually subtle and non-trivial, it's not clear that it can be done. But this is a way, a path, towards figuring out the initial conditions, even during reionization, which involves very messy astrophysics, of course. It relies on star formation. And then after reionization, if we map the distribution of galaxies where hydrogen still resides, so we know about the existence of damped Lyman alpha systems, and they are the dense pockets of residual hydrogen left over after reionization. We know that some fraction of the baryons were left behind in a neutral form, and we can use those to trace large-scale structure after reionization. And of course, we would like to test gravity to measure the growth of perturbations throughout cosmic history, either to be able to figure out if general relativity holds. That's obviously very important, but also in order to validate the standard cosmological model in terms of the matter composition of the universe. If matter is not just made of cold dark matter, weakly interacting massive particles, if it involves decaying particles or something else, you would get deviations from the standard gravitational growth that we expect. So we would like to do it in the redshift range between 1 and 15 that was not probed so far. And small-scale perturbations are still in the linear regime at these very high redshifts. So that's important. And the status of our field right now is analogous to the microwave background research about 20 years ago. Before COBE detected the anisotropies, everyone was putting upper limits. And that was the psychology. Even people that started to detect the signal preferred to announce in conferences upper limits, because there is always peer pressure. Nobody wants to deviate too much from the mainstream. So we are now putting upper limits, which is fine, but the moment there will be a detection, everyone, just like in the microwave background research, everyone will jump on the bandwagon, and there will be lots of detections, and then, of course, there would be more money to do future experiments. So the key right now is to have the first detection. And you might ask, from what we know, what do we expect in terms of the detection? Of course, we don't know yet the optical depth from Planck, but we know that the error bar is very small. And when you put a Planck person in a dark corner and you ask that person whether there is anything surprising in the Planck data, you hear that there is not much. There is nothing surprising. So either it illustrates the strength of mind of these Planck people, that even under interrogation they don't surrender valuable information, or indeed, I mean, it's only the error bars that are tiny, and the value is similar to WMAP. We can also use the Lyman alpha forest that we have at redshifts below 6, together with the optical depth, and ask, what are the likely values of the ionized fraction as a function of redshift. So you see the redshift here, 8, 9, 10, 11. And this is the probability distribution that you infer from a physical model that incorporates both the Lyman alpha forest and the microwave background data from a paper 2 years ago. And at high redshift, the gas is mostly, of course, neutral. So the ionized fraction is small. And at redshift of order 8, it's still very close. The ionized fraction is close to unity. And you can predict the expected 21 centimeter signal. It's way above the threshold for detection by the first generation of experiments. So we are optimistic that the signal can be detected, but we need to detect it. And of course, after it's detected, these probability distributions will be much narrower, as illustrated here. Now, the one thing I wanted to mention before closing is that the 21 centimeter line is not the only line, spectral line, that we can use for the purpose of mapping the matter distribution. In fact, there are many other lines. And so far, when people did spectroscopic surveys of galaxies, they always wanted to identify galaxies in those surveys. If you look at the Sloan Digital Sky Survey, they identify galaxies, and then they survey the distribution of matter on large scales, using the galaxies as tracers. And you might ask why. And I asked this question. I asked Daniel Eisenstein, who was my first student that I trained as a theorist, but now he's an observer. So in fact, he gave a very good answer that there are lots of stars that have emission lines. And unless you identify galaxies, these are stars in the foreground in our galaxy. Unless you identify galaxies, you can't really trust the intensity mapping. However, if you go into the radio, into very long wavelengths where stars do not emit, then this is feasible. You can do intensity mapping. You don't need to resolve individual galaxies because the foregrounds are not that much of a problem. And there are lots of lines that you can think of. For example, the C+ line is the most prominent line in our galaxy. COBE detected it very prominently. All of these lines, as you can tell, are related to heavy elements that were not produced in the Big Bang. So you have to rely on star formation supplying them. But you do have them in the local universe in abundance. And you can see here how many solar luminosities are emitted per star formation rate in solar masses per year in nearby galaxies. So these are typical numbers that one gets. And in fact, it was already observed by Herschel. This is from a star-forming region. You see all these CO lines observed. It's also observed in a galaxy like ARP-220 that is very star-forming. It's a star-burst galaxy. You see the CO lines. And of course, in M82, which is an interacting galaxy, you also see these lines. And together with Eli Wiesbal, we, back more than a year ago, we looked into the question of whether, for example, one can identify structure at high redshifts using such lines. And of course, the key is to use multiple lines. Because if you use one line, you might think that it comes from a specific redshift, but then it could be also another line that comes from a different redshift. And you will get contamination of the signal. You will measure the distribution of galaxies at two different redshifts mixed together. So one way to disentangle it is to look at two lines and cross-correlate them. So that if you have galaxies at a single redshift, they would emit both lines and you will get a very good cross-correlation. But if you look at another redshift, you will not get a good cross-correlation. So by cross-correlating two lines, you're able to remove the foregrounds from other lines. And these are the kind of error bars that one gets for CO lines that we calculated. You get even tighter error bars, depending on, of course, on the experimental setup that you imagine. This is for oxygen lines. You can actually measure this power spectrum as a function of K at a redshift of 6 to this kind of a precision. And one can design an experiment. I don't have time to get into the details. There was another very detailed paper by Leeds et al. That came out. And if one detects these CO lines, for example, one can cross-correlate them with the 21 centimeter line of hydrogen. And the locations of the galaxies, of course, will be anti-correlated with the location of the hydrogen, because the regions around galaxies will be ionized, and so you get galaxies where you don't get hydrogen. And you can figure out the characteristic size of ionized bubbles from the cross-correlation amplitude of 21 centimeter and CO. By now, there are about 5 papers on this subject, even though it started just a year ago. So I highly recommend for people to have a look into that, because it's also a very promising way of mapping the distribution of matter in the early universe. So in closing, let me just mention a few open problems, the way I see it in this field. Of course, we don't know the role of population 3 stars. It may well be that they are only of academic interest, that to make those very massive stars, you needed molecular hydrogen cooling and not much metal abundance. So as soon as there was some enrichment, these population 3 stars did not form anymore. So it's quite possible that the universe was ionized by stars like the ones we see nowadays. But we don't know that. And this is the holy grail of this, of the astrophysics of reionization would be to figure out if population 3 stars, these unusually massive stars, were responsible for reionization. And of course, they are much better factories for producing UV photons. So if we see that reionization started very early, one way to achieve that is through population 3 stars. Then, of course, there is the issue of the earliest X-ray sources. They are very important in heating up the intergalactic medium. And there are various possible sources. For example, X-ray binaries, high-mass X-ray binaries, associated with a black hole, accreting mass from a companion. And since the very first population of stars was massive, you might expect there to be a higher abundance of high-mass X-ray binaries compared to the local stellar population. And that would have important implications for the thermal history of the intergalactic medium, and especially the global 21-centimeter signal. And we don't know the answer to that, so we would like to figure it out. One way to figure out the abundance of black holes at early times would be to measure the population of gamma ray bursts that come from these redshifts. And one thing that is still missing in the literature involves simulations, numerical simulations of inhomogeneous X-ray heating. Sorry for the typo. Then, of course, there is an important question of how important was the opacity from mini-halos, galactic potential wells that were too shallow to allow gas cooling that would fragment into stars and so forth. So you can have these small halos, 10 to the 6 solar masses or less, capturing gas that does not fragment into stars, does not cool. And these mini-halos are very abundant, and they can absorb ionizing photons. Because of the high density of the gas, they have fast recombination in them. So they serve as sinks of ionizing photons. But of course, once they get ionized, the gas escapes from the shallow gravitational potential well. So they, by absorbing the UV photons, they commit suicide. They basically disappear. However, in the process of doing so, they consume a lot of ionizing photons, and they could affect the evolution of reionization. And we don't fully understand how significant they were. They could delay reionization by a redshift interval of 1 or 2 quite easily. Then it would be nice if we found radio-loud sources at high redshifts, for example, at redshift 10, because we can detect the 21-centimeter forest, just like detecting the Lyman alpha forest, except the 21-centimeter line has an optical depth of 1% compared to the optical depth of 1,000,000 for the Lyman alpha line. So we can, in principle, detect the universe when it was neutral at redshift 10 or above if we had bright enough radio sources. The problem is that quasars die out, bright quasars die out at redshifts above 6, and that gamma ray bursts have self-absorption, synchrotron self-absorption, at frequencies below 5 gigahertz intrinsically. So they don't emit gamma ray bursts. The afterglows of gamma ray bursts are not bright at 1.4 gigahertz that you need for the 21-centimeter line. Then, of course, all of us would like to find the best algorithm for removing foregrounds, which I didn't have time to discuss, but hopefully it will be discussed in the conference. And that's extremely important for the global signal, but also for the tomography, three-dimensional tomography. And then another interesting frontier that actually was not funded yet, although I find it to be very important, and that's detecting baryonic oscillations, baryonic acoustic oscillations, at redshifts between 1 and above. So above 1, instead of using galaxy surveys, using intensity mapping. And there are papers, theoretical papers on that, but somehow the funding agencies shied away from giving money in this direction, perhaps because the community that worked on baryonic acoustic oscillations were doing it in the optical, and they were more conservative. They didn't really fully understand the potential of the 21-centimeter mapping. The bottom line is we don't have funding. I think even in Canada we don't have, right, Whaley? Where is Whaley? We do? You're working on it. That's right. That was true 2 years ago. But again, it's not because of the lack of scientific merit. I think it's sociology, and much of the funding has to do with sociology of the field. So if, for example, this idea of mapping the baryonic oscillations would have emerged before the attempt to look at reionization, I think it would have been funded first. But just the fact that there were already funds allocated to intensity mapping at reionization prevented additional funds going in this direction. And of course, if there are exotic heating sources like dark matter annihilation, cosmic strings, and so forth, we would like to know about them. That's it. Thank you.